these are also evidence. You can see here how you will evolve from a point where everything's all connected to getting little offsets where the erosion is so much focused on the sides that the point is sort of left behind. And you get little rocks and so on left out at sea now as the erosion continues to move this way. These are the remains of old points that wave refraction has then created. These are called sea stacks. And some of them end up being very far out at sea, reflecting after millions of years, or hundreds of thousands to maybe millions of years of wave energy. Okay. We all like to live on beaches. If you think about all the energy that's gone into creating sea stacks and features such as this, obviously, no matter how wealthy you are, your house isn't going to do really well during storms and so on. Okay, so the beaches are obviously very high energy environments. All right. You can end up with interesting features like this, where houses that were once had nice views and were located somewhat close to the beach have now better views and are located really close to the beach, because clearly this pile of sand here, which is just uplifted material, very easy to erode, waves come in, and over relatively short periods of time, 30 years, you can end up with significant retreat of these uplifted shorelines. The ocean likes to erode things flat. Mountains tend to get eroded flat. Earth's surface, if you think about the equalization of potential energy, the Earth's surface wants to be flat. So beaches tend to be flat, or are in the process of becoming flat. Waves will erode. In the process of erosion, they'll make these promontories, they'll make these sea stacks and so on. But the end result of a sea stack is eventually going to be grains of sand that are going to be deposited flat. So when you see things that are flat, they're probably used to be under the ocean or in the process of being eroded and filling in gullies and so on and so forth. Here you can see here that we've got an uplifted shoreline. This flat surface right here, used to be down closer to sea level, but the tectonism and the geological processes have uplifted this area and moved it up out of the ocean, also exposing new material for erosion. Okay. You can see this as well through here. Nice flat surface. This is all at uplifted level. That used to be under. You can see these dipping, or these rock units on edge. Here are the same ones in the foreground on edge. And you can see that if you can imagine if you were to lift this up, all right, with an earthquake or as a single event or many earthquakes over thousands of years, you could create this. Nice flat surface with trees on it and so on. Okay, so as I just said, consider continued uplift. This will eventually become that, and we have a continuum process of these beaches just get continually uplifted. If you're from California, you've driven along Route 1, there's a lot of crops that are planted in Santa Monica, Santa Barbara, along that whole sort of area. And they're flat. They're very fertile because there's a lot of organic matter there. And the soil is very easily plowed and made into agricultural farmland. And you can see this right along here along Santa Barbara. You can imagine how this would be a very productive area for farming. Okay. All right. Other examples of wave-cut benches. Palos Verdes. There's the shoreline. And this is all at one elevation. And notice this photograph. There's one area And that was the wave cut bench. This is another one. That's another wave cut bench. And you can see how there's, I'm a little too close to it, 1, 2, 3, maybe a fourth off to the side here. Levels of how this has been continually uplifted. And if this continues, this here will get uplifted slowly, and we'll have this bench here will look just like that. And we'll have another flat area here, and the beach will be that way. All right, here's what one looks like from the side, Palos Verdes. Other examples, repeated rises and falls of sea level. On the east coast here, submerged shorelines. Looking at the other side of the coin, instead of material rising up, here we might have either sea level rise or the land falling down, and the ocean is encroaching progressively inland. Often these submerged shorelines lead to what we call estuaries. And an estuary, defined here as an ocean or a sea-flooded river valley. So you imagine a river emptying into the ocean. If that sea level rises or the land surface drops, the ocean is going to progressively move up that river valley. You get progressively higher up that river channel. Okay? And that leads to, on a large scale, things like the Delaware Bay estuary or the Chesapeake Bay estuary, or if you're in England, the Thames estuary that London's on. All right? These large estuaries, and you can just see how rivers are coming down, little rivers. This was the big river here. This is the river here. And as sea level has risen, it has progressively flooded and created this large-scale estuary. All right? Very dynamic environment indeed. This also leads to, if we combine our thoughts to imagine that all that energy that we talked about in the context of waves, all those wave energy, storms, and just regular daily waves is going to be moving a lot of sediment around. Okay? And this sediment is going to be deposited along beach spits and create what are called barrier islands along the shoreline. And here we're also going to, it's important to remember what we talked about in the sense of longshore drift. So here we've got, this might be the, this looks like it's the classic example in Barnstable on the north side of Cape Cod, inside Cape Cod Bay. Although the direction is wrong. This looks like this, okay. Here, let's look at this left side of the diagram first. Okay? If we imagine longshore drift going from left to right, sand grains moving down, it's going to slowly just start building out a spit out in this direction. As you can see, progressively, sometimes it might get too skinny and you'll have a channel open up and come through here. All right? Here you can see it, so clearly in this direction, the longshore, in this case, the longshore drift is moving from the bottom of the diagram to the top of the diagram. In this direction, it's going from left, this example going from left to right. Right. Yeah, this is actually Barnstable, moving it in this direction here. All right, curling around, deep channel, see the spit even coming along up in the air. Here you have a combination of processes going on. If you will, this is the south side of Martha's Vineyard. If you will, forget about this beach. Imagine this beach isn't here. Right? Initially, these are just little rivers coming out of the main part of Martha's Vineyard up here. And these are just rivers, and as sea level rose, you're creating sort of mini estuaries. Okay? You can see that just visually how that case might be here and here. Well, now, let's think about, all right, well, we do have longshore drift. We do have erosion going on. Sand is going to be rolling down and being deposited in front of these, blocking them off. And now we have the great ponds. These are called great ponds of Martha's Vineyard. Beautiful beaches, track behind it a pond. Okay? The pond is the result of sea level rise, filling in the old river channel, and the beach is due to longshore drift, erosion of cliffs, and transport of sediment. All right? Similar example down in Baja. Here's a sand spit in front of a mouth of a bay. All right? This is in, this looks to me like Duxbury and Plymouth. All right, so Boston is up here. We've got an estuary behind a sand spit with longshore transport in this direction. Okay. Other examples in Rhode Island. Here you've got, behind it, you've got the pond. That's essentially an estuary, and then the sand spit down in front. Okay. So these submerged shorelines, as you submerge, you're adding all that energy, that beach energy, into areas that it didn't used to be, right? The beaches are moving inland, eroding as they go, and you end up with a lot of beaches. The reason why there's a lot of beaches in Massachusetts, Cape Cod, and Rhode Island, and Connecticut, New Jersey, all that sort of thing, is we're eroding as we go, and we're creating all that sand, and then it's getting migrating along shore in response to the currents. And there's so much sand, there's literally just piles of it. Piles of sand that we call beach dunes. Okay. Back to more discussion on groins. Okay. Groins in the New Jersey shore. Nice picture, you can see repeated examples of it. Longshore drift coming from the top of the diagram down in this way here. Okay. Hundreds of miles of these up and down the east coast of the U.S. These are very vulnerable areas, obviously, in terms of hurricanes and bad storm activity. South side of Long Island, here's Fire Island. All of this are these barrier islands, and behind it you've got the large estuaries. So they happen at many different scales. Little ponds on Martha's Vineyard, or certainly on the south side of Long Island, the New Jersey shore, or what have you. Other examples that are well known, unfortunately, mostly because we hear about these places in the context of storms and damage. But here's the Outer Banks and so on of North Carolina and South Carolina. Here's the Gulf Coast of Texas. These are all places that get very much affected during storms. And you can see here how this is, as sea level rises and the shorelines are moving inward, we're getting more and more submerged, leading to these barrier islands out here, and the progression of water, seawater moving more and more inland. All right, so where do you want to live, A or B? This is a map view. These are fish lying on their side. Where do you want to live, A or B? Personally, I wouldn't want to live anywhere on these things. I'd like to live a mile inland and walk to the beach. But I think I'd take B. Why? B is going to be here for longer, because this is going to keep growing in this direction, and B is going to be here for longer. It's going to go and keep going, and this channel might start migrating in this direction. Right? Very dynamic. You might think that it's okay to build a house there. It's going to be there for what, 20, 30 years? Believe me, 20, 30 years goes faster than you think. All right, let's move into some hurricanes. I hope I got the volume up on this thing. All right. Hurricanes obviously are large, subtropical, tropical cyclones. Wind direction is counterclockwise in the northern hemisphere. And I want to emphasize the point about large. And you know they're large and all this sort of thing, but look at that picture, and that single storm is essentially the size of half of the Gulf of Mexico. And it's drawing in water and moisture all the way down into the Pacific Ocean and having an effect probably out into the Atlantic Ocean as well. these things can affect at any one point. If you look at this wind pattern here, these storms can affect upwards of 10 to 15% of the Earth's surface in one fell swoop. All right. This is a diagram showing temperature profiling here. As you probably heard or are aware, hurricanes gather their energy from warm surface ocean. And you can see that the warm air coming in, and it's becoming more and more cold as you get to the center of the hurricane. That heat loss is turned into energy, and that energy is promulgated and manifest by high winds in this rotating environment. So the loss of heat that you're seeing from the outside in is the exact opposite of wind speed increasing as you go. So you're losing heat and gaining wind. You may have heard about hurricane scales. Like around here last week, we had, a couple days ago, we had wind speeds of 35, 40 miles an hour, and that was pretty windy, wasn't it? Okay. If you have sustained winds of 74 to 95, that's a hurricane class 1. Look at some of these classifications all the way up to class 5, winds in excess of 156 miles an hour, and read this sort of destruction level: complete roof failure, complete building failures, utility buildings blown away, flooding causes major damage, massive evacuation of those residential areas, and so on. Katrina, which is unfortunately the sort of storm of record of our lifetime so far, although I'm sure there'll be more Katrinas or worse. Here we have, in terms of, if you just look at this here, the NHC stands for National Hurricane Center. That's their prediction, and these are predictive envelopes. That's 10% or 90% confidence interval. If you look at it from 10 to 10, they're 80% sure that this thing is going to be between here and here. But look at those wind speeds, miles per hour, on the order of 160 to 170 miles an hour. All right? And here we have the predicted wind speed of at least 39 miles an hour as a predicted envelope as the storm moves across Louisiana and then dies out, eventually coming up into New England. So let's take a look at some interesting pictures as the storms are approaching. All right, lots of small storms associated with the larger scale hurricane itself. Tornadoes associated as well. People think, oh, tornadoes or hurricanes. The thing about a hurricane is it's both, because there's tornadoes in there, which it's not like you're ever going to notice because you're in your basement praying to Jesus and Jerry Garcia all at once. All right. So here we have New Orleans. You've obviously heard about New Orleans being essentially decimated with Hurricane Katrina. I hadn't seen this diagram before an hour and a half ago, so I really like it, though. It opened my eyes a lot in one characteristic way. Look at this cross-section. This is the Mississippi River. This is Lake Pontchartrain, which is the lake just north of New Orleans. So here's the river. That is New Orleans. Now, I might be just an oceanographer, but to me, that's not the place I would build my city, because it's below the water level of the Mississippi River and below the water level of Lake Pontchartrain. And of course, we've got these flood walls, levees, dikes, keeping the river and the lake out of my city. It's not rocket science. Water flows downhill. City downhill. Water flow onto city. Done. Okay? Now, I'm obviously trivializing it and making it seem easier, but that is really basically it. People wonder what happened in New Orleans. That's what happened in New Orleans. All right? And you put a big storm on top of this, and you break these walls. There you go. Break the walls, in comes the water. Break the walls, in comes the water. Flood out essentially the entire place. Okay? Flood out dead people. Flood out live people. So that's the Superdome. And as you're probably aware, world's largest disaster center. I can't just say entire city blocks. Anybody here from New Orleans by any chance? All right. Can't just say entire city blocks. Entire neighborhoods. Entire aspects of the city. It's not like we just flooded out the Back Bay. It would be like we flooded out all of South Boston, and the Back Bay, and Dorchester, and Brighton, and Alston, and Cambridge. Cambridge, who needs them anyways? Right? Somerville. This sort of scale of flooding because of that. Here's before. I'm not sure which is before and after. This is like flood, and then after the flood went away, or before the flood, and then as the flood comes in. But you can just see the depth of this. I mean, here are regular bridges going across this canal, and it's all underwater there. All right. Now, this is running. Can I get noise? How can I get noise on this thing? Lawford's going to kill me if I don't get noise on this. Sorry, Lawford, on video, I'm not getting noise. Yeah, pretty impressive. Not a good time to be out in the boat. Okay, let's do this again. Let's look at some things. Obviously, it's windy, but the scale of some of these things going by, that's a roof. All right. Obviously, signs like that are going to be broken up. Sorry. All right. Some of the large images of things that you can see are big pieces of corrugated metal, the tops of gas stations. All right. Commonly, you have the gas pumps and then this thing to keep you out of the rain. That's just this big wind that's going to go by. You got this picture of a house coming up. There you go. There goes the whole roof. And obviously, lots of boats and things like that getting hurt too. I'm sorry, I can't get the noise. I can't get the noise. I don't know what's going on. All right. Okay. So this is exacerbated by the fact that we are starving New Orleans and the southern part of Louisiana in terms of its sediment supply. Because for millions of years we've been eroding away the inland part of the United States, and all that sediment has been coming down the Mississippi River and allowed to migrate. The river mouth has been allowed to migrate and deposit sediment all throughout this area for millions of years. Now, migrating rivers and all that sort of thing, very hard for mankind to deal with. And so what we've been doing for the last hundreds of years, last 100 years or so, is channelizing the Mississippi River so all that sediment supply bypasses the delta area and the sediment just gets dumped out here. It's not allowed to replenish this sort of area. We've also been extracting tremendous amounts of oil and gas from the whole overall area here, and that's caused, as well as water, drinking water, and that's caused the area to subside. So we really hit it with a double whammy. We've extracted materials and we've affected it such that the land surface is going to go down, and we've also cut off the sediment supply, so there's nothing there that's going to be added to it to replenish this material with new sediment. So what's going on here, if you look down here, for example, as you can see, Louisiana has lost 1,900 square miles of land since 1932. All right? We're losing on average, 24 square miles of land per year for each of the last 50 years, in other words. Okay? That ends up, if you blow this up, you can see the original coastline here, and now you can see the water moving more progressively inward. All right? Okay. So, as the water comes in, that means the storm water comes in even more. It's all a gradation. Interstate 90. Boats in a car parking lot. They're going to get ticketed. Okay. I can't. All right. That's a tornado. Some more images here. I'm going to fiddle with this. Oh. Any noise? All right, I can't get that volume going, so I'm going to jump. Sorry, folks. Okay. Yellow dots are evacuated oil rigs. Now, I like this slide for a couple reasons. One reason is we always focus on what's going on land, but there were a lot of people out on these oil rigs. They all had to get evacuated, and all these storms that go on down there, there's thousands and thousands of men and women working at sea on oil rigs that are at grave risk for any of these large-scale storms. Okay? Secondly is this graphically shows you all the extraction of resources that's going on in this area. When I talk about the land surface being lowered because of it, you sort of get a good feeling for that here. Okay. Right after Katrina, a month and a half later or so, there was Rita that came in. Fortunately, Rita did not hit Louisiana. It was projected to go along here. It came along in this direction here. Still caused some problems. There you go. That looks pretty cut, actually. Not into the tattoos, though. Lots of evacuations again on that. All right. Now, this is an interesting diagram. We are not immune to hurricanes here, as you can see up in this area. All right? But by far, most of the hurricanes happen down in this part, at least in the United States. We spoke about some of these here, but this area here is also very vulnerable. And what do all these areas have in common? Well, 15 minutes ago, I was showing you all sorts of slides about sea level rising, right? And longshore drift and barrier islands and all this sort of stuff. So it's not like hurricanes are hitting in a, or excuse me, put that in the positive. Hurricanes are hitting in a very vulnerable aspect of our shoreline to begin with. Okay? Hurricane Andrew came across Florida. This is the one that took out Homestead Air Force Base and a lot of Miami. All right? Kept going. All right? Path right across Florida and had large impact on Texas as well. Here's a snapshot in 1998 showing that during hurricane season, you can see there's all sorts of hurricane activity going on. They are coming from Africa, moving across the east, from the eastern part of the Atlantic across here, and various pathways move up in this direction like this. However, also notice what's going on out in the Pacific Ocean, because there's hurricanes and storms in that area as well, okay, which I'll get to in a bit. Here are some shots, again, same story, of Hurricane Isabel, offshore of North Carolina. Now again, look at the scale of this. This is us right here. All right? This is Georgia. So the entire eastern seaboard is affected by this one storm. large flooding. You can't even see Long Island. So you think of this area, think of this storm hitting North Carolina. You can't even see Long Island. It's underneath this storm too. So the same processes going on that are affecting Long Island, New Jersey, and so on. All right. This is just 1999 alone. All right. 1999 alone. Here we've got barrier beaches and so on. I just showed you this sort of area. And it was crisscrossed by hurricanes in that particular season. As I said before, they're also out in the Pacific. All right, here's Baja California. Here's Mexico. Hurricane Ignacio, 2003. Okay. Now, how many people died in Katrina? Anybody know? Roughly? Do you think it was more or less than 77,738? It was a lot less. I don't know the number offhand, but I probably maybe 100, if that. Probably less. Do you guys happen to know? Okay. Now, if you're one of those 100, of course, it doesn't matter how many other people are dead because you're dead. It kind of sucks. But, you know, still only 30, 40, 50 people or what have you in Katrina. Essentially a similar storm except with far less wind speed. Okay. In Burma, Myanmar, 80,000 people were killed. All right. This is the path of the storm. So here's India. All right, Indonesia. All right, Singapore, Thailand, and so on. Here's the path of the storm. The size of the dot shows how the storm is strengthening. Came right across this area. It's all lowlands. Obviously very poor people overall. The country is not nearly as well put together in terms of infrastructure. And I'll show you some photographs of this going on in a second as it hits there. So, one important point about the storm is that the storm itself is moving in a direction, and the wind is also rotating in a direction. All right? So, as the storm is moving in this direction, and the wind is moving in the same direction, you have the additive wind speed here. So if the wind's blowing at 100 miles an hour, and the storm is moving at 20 miles an hour, you got 120 mile an hour winds over here. If the storm is moving 20 miles an hour, and the wind is blowing 100 miles an hour that way, on the other side of the storm, the net is only 80. So on one side of the storm, the wind speed is significantly greater because you add together the wind speed plus the storm motion. And on the other side of the storm, the wind speed is less because you subtract the storm motion from the wind speed. So it matters on which side of the storm you're located in terms of the impact. And so if you go back to, say, here, okay, this quadrant of the storm is much more destructive than this quadrant. You can see how the wind is rotating like this. The storm is headed in this direction. You've got 100 miles an hour of wind plus 20 miles an hour of storm. Over here, your net is going to be 120. And over here, your net's going to be 80. So right on either side of the eye of the storm, you could have a difference of 50 miles an hour of wind speed. And that's often the difference between life or death or the destruction of a storm. For example, if Katrina had been slightly to the west, the damage would have been much worse for New Orleans, because New Orleans would have been on the worst side of the storm. Okay? All right. So here's some pictures from the Burma hurricane. Clearly, massive amounts of destruction from water and wind. All right. And in one of the sort of the tragedies of this particular storm, the Myanmar government is not progressive. It's a military dictatorship, and they're extremely closed and extremely paranoid about external influence. and they did not allow foreign aid to come into their country for the first week or so, or even maybe even 2 weeks. And so there was a lot more loss of life than there needed to be. Okay. All right, I am going to stop there because we're at a convenient stopping point. All right.